For our project, we wanted to turn the Freedom Board into a magic wand that could render spells onto the screen, by calculating two-dimensional displacement via the accelerometer sensor on the board. We achieved our goal of creating a real-time on-screen rendering of the board movement, translating into displacement on the plane perpendicular to the ground. Our initial proposal included reach goals that included being able to draw shapes and even classify these shapes to register them as spells. We quickly realized that the accelerometer was simply not sensitive enough to create smooth enough data for drawing recognizable shapes that could be classified by standard shape classifiers. So in the place of the shape goal, we decided to make the wand more visually interesting using the onboard LEDs.
To make the wand feel more interactive, we decided to use the LED on the Freedom Board. When the board senses acceleration on the x-axis, the LED turns red. When it senses movement on the z-axis, it turns blue. When moving diagonally, both colors can turn on, resulting in a purple color. The colors will smoothly fade out over time to give it a more magical effect. The smooth transition period was achieved using two different interrupts, one to flash the colors for different lengths of time, and one to decrement the time for each color. The most difficult part of implementing the LEDs was figuring out the load values for the interrupts. Sometimes, the interrupt that flashed the colors would happen too frequently, resulting in it interrupting itself and preventing the board from actually sending data through the serial.
After collecting accelerometer data on the board and performing all the necessary calculations, we need to send this data over to our computers for visualization. In order to do this, we've decided to use UART, or serial connection, and send at a frequency of 60 Hz, since that's the regular screen refresh rate of a computer. We've chosen the same baud rate on both ends, which is 9600, and we've decided on a data packet structure, which is basically the x-coordinate of position, comma, the y-coordinate of position, followed by the end-of-line character. We're not too worried about drop packets in this case, since we're using a serial connection and that's pretty reliable. Now on the Python side, we're using the PySerial library to read in this data. The PySerial library just makes it really easy to read stuff in, and since we're including the end-of-line character, we can simply call the readLine function, and then parse the data by splitting where the comma is. In order to visualize the data, we're using the tkinter library, which is a built-in Python GUI library. We've created a window class which implements all of the features we want, like a title, a description, and we've also embedded in a matplotlib graph in order to visualize the plot of our position data. We did run into one issue during this though, was that the tkinter library requires us to call the main loop function in order to keep the window open. Now this main loop function is blocking, so we aren't able to concurrently keep checking the serial line for new data. We've thought about a couple solutions to this problem, one of which was to use multi-threading, but in the end, we decided that the most simple option was to basically rewrite the main loop function. In order to do this, we found the necessary library calls to simulate the behavior in the main loop function, and then we also added in all the checks for the new serial data inside of that loop. So now we can just call that function instead of the blocking main loop function to have the GUI refresh and also checking for new data happen simultaneously or concurrently. We're storing the data in a list with a maximum capacity of 100 data entries, which means that once it exceeds the maximum, we're just popping off the oldest data that came in. That way, on a GUI, we're only displaying the 100 most recent data entries. And that is basically how our front end works.
When implementing the magic wand, we didn't use any external libraries, but we did use the example accelerometer code provided by the TAs. External code that aided us in this project included a Python algorithm for calculating a moving average over an array, which we implemented in C using linked lists. This moving average served as a simple low-pass filter to decrease noise in the accelerometer data. In order to approximate the integration of our acceleration and velocity functions to get displacement, we used an equation described in an article about measuring the vertical displacement of an elevator using an accelerometer. The running calculations for velocity and displacement were also handled with linked lists. So the final project had a linked list representing raw acceleration data, averaged acceleration data, calculated velocity, and calculated displacement. In order to not spam the Python script unnecessarily, we also have an interrupt that handles sending data over UART at 60 Hz to match the monitor refresh rate. This was a project that really forced us to not only draw from what we had learned in labs, but to do a lot of outside research on our own about how to mitigate issues with sensor noise and serial communication, which made it challenging but also quite fun. So yeah, hopefully this doesn't Avada Kedavra our 3420 grade. Thank you for watching.